Hello and welcome to another video on orbital mechanics. I am working through the book Orbital Mechanics for Engineering Students by Howard D. Curtis, 4th edition, and we're going through the questions, but in this video I'm going to go through some of the theory on orbits and deriving a lot of the equations for an elliptical orbit. An elliptical orbit is a non-circular orbit, shaped a bit like an egg, and you have a whole bunch of properties for this orbit. You have the focal points of the orbit, and in a circle, those focal points are in the center. As the circle turns more elliptical, the focal points drift outwards. And this is actually how you make an ellipse. You put 2 points on your focus points, and then you wrap a string around it, and you pull the string around, and you get an ellipse. And because the string is taut as it goes around, every point on the circumference, the string is the same length. And it is, in terms of this diagram, that length is 2a. So a is the length of the string here and here, because that's down the middle. And it's also the length from here to here. So that's a, and that is a as well. And if you're up here, this plus this, again, is 2a. The ratio between the width and the height, from those two values, you can derive a value for the eccentricity, which is basically a value telling you how wide it is compared to the height. And we can derive that eccentricity by looking at this line here. So the distance between the focal point is 2ae. And if that was a circle, the distance would be 0 because they'd both be in the center. So e would be 0. So when it's a circle, the eccentricity is 0. And when it's greater than or equal to 1, it's a parabolic orbit, which doesn't have a closed loop. So in order to get this 2ae, we can just take this part here, which is 2a, and that's a right-angled triangle. So we can just use our Pythagoras theorem to get e there. Square root of 1 minus b squared over a squared. Now in this particular example, I've used some simple numbers just so I could draw it to scale. So I've got a as 8 centimeters, b as 4 centimeters, and the eccentricity that comes out nicely to square root of 3 over 2. Something else to note in this is this value here is the gravitational constant times the mass of your main object, and the angular momentum per unit mass is r cross the radius of your r cross product the velocity. That's a constant because angular momentum is conserved. This is your periapsis, this is your aoapsis, and this is your apse line. So in order to get this value from this diagram, we can use the cosine rule. So we can say r prime squared equals r squared plus 2ae squared plus 2ae cos theta. And we also know that r plus r prime equals 2a, so we can put that back in there, rearrange it, cancel some terms, and we end up with r equals a upon minus 1 e squared divided by 1 plus e cos theta. So if you have theta and you have your a and e, you can get your r. And then there is another equation that's very similar, which is here, and I'm going to pull over something to derive that. So I'm going to bring this over. So we have, earlier on in the chapters, we have the acceleration equals u divided by r cubed times vector r in a minus to show that the direction is towards the center, a decreasing radius. And what in the book, it cross multiplies both sides with the angular momentum vector per unit mass. And they're just doing that to remove components and simplify it. And when they work that out, they come to, look in the book, it's not particularly long, but it's not worth going through right now. But when you do that, you come to this equation here, which is the derivative of the velocity cross with the angular momentum per unit time minus u and the r vector over the, it just comes out to be r again, I think. But that is a constant, that derivative. So that's zero, sorry, that derivative is zero. So we know the value inside it is constant. So then we end up with velocity cross multiplied angular momentum minus u r vector over r equals c. And this c is called the Laplace vector, but I wouldn't worry too much about that. There's a description in the book of it, and it's on the orbital plane. And the eccentricity vector equals the Laplace vector divided by u. And so that's that. And then from here, we can show that this c is on an orbital plane, but let's not worry about that. From this point here, we can go down here. We rearrange it with e, so we can get this. Simply rearrange that to get this. And then what they did in the book is take the dot product with the radius vector again to make it scalar. So we end up with, that cancels into r, and this cancels into h squared, and we end up with r plus r dot e equals h squared over u, and r dot e equals re cos theta. And then plugging that in there, we get r equals h squared over u times 1 over 1 plus e cos theta. That's that equation. So going back to our main page, here it is here. So we have these two on 2. And from this, we can say that h squared over u equals a upon 1 minus e squared, right? Because that there, right, and that there are essentially sitting in the same place. We can just say that's true. We'll use that later. And then the next stage is to use this equation of energy in the orbit, which I'm not going to go into how this is derived, but it does make sense. So the energy of the orbit is velocity squared over 2, and this is essentially your half mv squared kinetic energy. Now the n's have been cancelled out, so that's why it's v squared over 2. And then minus your potential energy, and this u is gravitational constant times mass divided by r, so that's your potential energy, because that's the orbital equation. So, and the m is cancelled out. So you can imagine if r was very big, you'd be very far away. This piece would drop to 0, and you'd just be left with a constant velocity, unperturbed by the gravity. As r reduces, this grows quicker, and you're going to be speeding up as well. So this is going to be growing exponentially as you get closer and closer. Velocity is going to be increasing as it compensates for this growing value, reducing this. This needs to balance the energy. So as r decreases, this value increases. This is a negative sign, so this has to be even bigger. So your velocity is growing. So this makes sense, right? Now at the periapsis here, so if you say we're at the periapsis, we'll just replace v with vp and r with rp. The velocity is just tangential, right? It's only going that direction or that direction, right? So given that it's tangential, we can say that the angular momentum divided by radius is equal to that, and that's just your angular momentum equation. So that's fine. And then if we take the radius in this form at the periapsis, which we can get by just simply setting theta equals 0, we'll get this equation. So if we take this and put it there, we will get this h squared over rp squared, radius periapsis squared. And then if we take this and put it into these, God knows how God came up with this stuff. I assume they just played with it until something nice came out. So you end up, so you place that in, and then you simplify and rearrange, albeit it's quite a fiddly one. You get this equation here for energy. So now we have two equations for energy. We have this one, and we have this one. And if we take this equation here, and we replace it here, plug it in here, as you can see, we've got quite a few similar terms, right? So you can plug that in quite easily. You end up with minus u over 2a, which we can equate back to this one here. So it equals v squared over 2 minus u over r. And then that, therefore, after rearranging that, we have this very well-known equation, which is v equals square root of u upon 2 over r minus 1 over a. And that is quite a lot of equations that you can use to more or less, given enough information, you should be able to get all the properties of this orbit. If you're only given velocity and radius, as you'll see in a minute, you can get h here, and you can get a here, because this only has three variables, only there's that's constant, that's constant. So if you get these two, you can get a, and then if you've got a and you've got h, you can get e here, and from e and a you can get b. So from these equations you should be able to get anything out of it, and this is, you know, the first time I've seen it all on one page, so that's hopefully clear. If it's not clear, leave a comment below, or if you think I've made a mistake anywhere, let me know. Thank you very much. Goodbye.